Good morning or good afternoon. Welcome to our latest Full Stream Ahead webinar, and thank you for joining us. If we have not met, I'm Carrie Fellers, the Director of Membership here at Geothermal Rising, and I'm delighted to be your moderator today. We have some amazing speakers on surface innovation, but before we introduce them, I want to begin with a few announcements. We want to thank our members for your continued support. Your membership helps us continue our mission to build and strengthen the geothermal industry, and we appreciate it. Let me walk through a couple of our members. Thank you to our Earth Energy visionaries, Baker Hughes, Calpine, Ever, Exceed Geoenergy, Quays, SLB, and Turboden. And then our geothermal champions, Burns and McDonnell, COSO, BHE Renewables, Chevron, AgGeo, Expro, Fervo Energy, Halliburton, Curita, Neighbors, NOV, Ormat, Oxy, Sinclair, and Southern Company. And our clean energy enthusiast, Amoresco, Baseload Capital, Central Washington University, DTEC Rotary Steerables, Geologica, NREL, Valoric New Energies, XGS Energy, and Zanskar. So our next Full Stream Ahead will be here in a few weeks on April the 22nd. It's going to be on EGS, and we'll have Utah Forge, Baker Hughes, and Fervo presenting on some of their advancements. So we certainly invite you to attend that. And then we have a number of upcoming events. Image, the Geothermal Hub, our Indigenous Geothermal Symposium, the Geothermal Discovery Day, which is new this year. That will be a family day at the local museum there in Reno and open to anyone that would like to attend. You just need to register. It's free. We'd love to see you there. And then our annual Geothermal Rising Conference will be there in Reno in October. Our Thermal Energy Networks now is going to be in Baltimore, Maryland in March of 2026. And our Geothermal Investment Forum will be here in Houston in April, and our Capitol Hill Day will be in Washington in 2026. We hope to see you at some of those events. So it is my pleasure now to introduce our speakers. I am going to introduce Justin. I'm going to introduce Justin. And I would also invite you to ask your questions in the chat in the Q&A section. We're delighted to follow up with those after our presentations. So Justin is an emerging technology manager at Burns & McDonnell. Justin focuses on market and opportunity development for generation and decarbonization technologies. Throughout his nearly 20-year career, Justin has been focused on the development of generation projects. Prior to his current role, Justin managed Burns & McDonnell's development group, supporting power generators across all aspects and throughout the full. Oh, I'm so sorry. That is incorrect. We're going to start with Joseph. Joseph Bonafin holds a master's degree in technical engineering with a specialization in power generation systems. He joined Turboden and Mitsubishi Heavy Industries Group company in 2009 and has since accumulated extensive experience in business and product development. As a director of the Next Generation Geothermal, Joseph leads global projects, overseeing every phase from early technical development to the finalization of commercial negotiations. A strong advocate for innovation, Joseph has played a pivotal role in implementing some of the world's most advanced, or first advanced and enhanced geothermal projects. His expertise in geothermal power plants and turnkey projects has contributed to groundbreaking advancements in the industry on a global scale. So it is my pleasure then to turn it over to Joseph from Turboden.
Thank you, Carrie. Hi, everybody. And thanks for hosting myself and Turboden for today's webcast. Let me share my screen and start with the slide deck. Okay. Is that working?
Yes.
All right. Okay. Thank you. So a few words about who we are at Turboden. We are one of the pioneers of organic ranking cycle technology. The company was founded in 1980. And so far, we have accumulated experience in more than 50 countries worldwide. So all the dark gray colored countries in the map, you can see have at least one Turboden power plant as of today, so more than 460 power plants, with overall capacity installed of exceeding 1 gigawatt. We are present in most of the renewables energies, including geothermal, of course, and we are also dealing with heat decarbonization with our proprietary large heat pumps. And since 2013, we are part of one of the largest corporates for power industry in the world, which is Mitsubishi Heavy Industries. We are present in North America and Canada with different references, so power plants in operation and under construction. And we have also a subsidiary in Canada, in Calgary, and recently opened an office in Houston, Turboden America LLC. So what we do, we are used to manage complex and large projects. So this picture shows our lightning dock geothermal power plant that was delivered in New Mexico in 2018. Originally installed by, developed by CIRC and now acquired by Zanskar. So we are dealing with all the phases throughout the surface technology design and implementation. So we are leading the design of the thermodynamic process, the control philosophy, and also we have our proprietary axial turbines. So all our plants have a Turboden turbine in operation. We are in charge of selecting the most suitable working fluid among a wide portfolio of fluids. And the control system is fully automatic for operation also in remote areas, and possibility to have island mode operation. So the key components in the power plant, including the heat exchangers, their cool condensers, are fully specified by Turboden. We manufacture our proprietary air cool condenser, and we deal with a number of possible partners for the integration of the surface turbo generator at site. So typically EPC companies such as BMEC are the partners that are integrating, taking care of mechanical, electrical, erection, civil works, and connection to the existing facilities such as the wells. So a few words about the process. You should be familiar with the binary, or also called organic Rankine cycle. It's a very mature and proven technology that converts the heat from a hot source. I would say ranging from 100 degrees Celsius up to 500 degrees C. This can be a stream of hot water, steam, a mixture of steam and water, or flue gases, or thermal oil, according to the type of heat source. Looking at geothermal, we are considering brine as hot source. So the heat is getting in the closed loop, in the process, in the RC process, by means of heat exchange with heat exchangers. There is a turbine that is spinning and generates electricity thanks to an electric generator, and the working fluid after expansion in the turbine is then condensed by means of a condenser, can be an air cool condenser or a water cool condenser, and then pumped back in the heat exchangers. The reverse process is the large heat pump process. So instead of a turbine, you have a compressor, and that is also one of the pillars of the decarbonization mission that we have, and I will talk more about that later. A few statistics about ORC technology. So this outlook shows the last 10 years for turbine additions in geothermal industry. So all of these include binary turbines or sea turbines, or the traditional steam turbine, single, double, triple flash, dry steam, or back pressure. So you can see that the shares are widely dominated by the ORC technology, 60% versus 40 in the last 10 years. And the average capacity here is about 9 megawatt, whereas the traditional steam turbines have an average capacity of 38 megawatt. I would say that this 9 is getting larger and larger, and also this average includes many projects below 1 megawatt, so it's a little bit an outlier. So here we see that from 2015 to 2025, binary has almost taken double up with its shares, eroding the steam turbine shares in the overall power plant market. One should ask why this is going on. But before telling that, I would like to say that the capacity is scaling up because the market is asking for larger ORC turbines, and that's the projection over the last 30 years of how the capacity, the shaft power of our turbines has increased from few hundred kilowatts up to 45 megawatts of the current projects now in under construction. And the current development shows that there is a market demand for larger turbines, also exceeding the 60 megawatt for the future projects. So going back to why ORC is eroding the traditional steam turbine market is because there is definitely a higher flexibility in exploiting a wider range of temperatures. And that's just a matter of selecting the most suitable working fluid. Turboden is the company with the largest portfolio of working fluids. And here in this chart, you see in a chart with temperatures and saturation curve. So that's entropy. Basically, that the critical point of these molecula that are low boiling working fluids is always in between the typical geothermal range of wellhead temperature. So from 100 degrees up to 250. So it's just a matter of selecting the molecule that has the closest temperature at the critical point to the wellhead temperature. That's because the thermodynamic process will be greatly optimized by doing so. The efficiency is a function of temperature. This is true in every type of thermodynamic application. So that's because of Carnot rule of thermodynamics. And I just wanted to divide among different categories the so-called high temperature or high enthalpy fields, medium and low, that are characterized by different wellhead temperatures and different reinjection conditions. What could look like the gross and in brackets net efficiency. That means how much power output you get from your ORC process as a ratio of how much thermal input you provide in the system. So let's say that EGS projects or Western USA projects have a wellhead temperature that is close to 200 degrees. So a well-optimized ORC process can target efficiencies of 20%. That means you take out from the well, you extract from the well 100 units of heat, you generate 20 units of electricity. So going to the components in a power plant, there is a clear division between underground technology, so drilling and wellheads. That's not part of our scope, but also among the surface technologies, we are dealing basically with the design and the procurement and commissioning of the core power plant components, so the turbo generator scope. That is where we implement our innovation throughout all the projects. And the remaining items will be explained by the colleague of BMEC regarding all the surface facilities. We focus on the electrical grid with all the utilities and items that are required to put online a turbine with an electric generator that generates continuously electricity. So just a quick outlook of an aerial top view of one of our plants. That's a 5 megawatt plant in operation in Germany since 15 years. And the biggest footprint is taken by the air-cooled condenser. The turbine generator are quite compact. Heat exchangers are here. So this is quite a compact wellhead unit with all the facilities very close to the production and the reinjection wells. This is based just on a doublet of wells. Then it's important also to have a control room with all the for the operator to get live acquisition of the data. In fact, our plants are fully automated, and they can be completely turned on and off from remote, get all the diagnostics, troubleshooting, and also we are implementing proprietary machine learning tools to predict when is the time to have a substitution of critical components, such as for the rotating parts, the bearings or the seals. So going to a few references. This is a large-scale project that was implemented in the Philippines. It's in operation since 2024, and that's a water-cooled plant based on traditional geothermal source. It's a 29 megawatt single generator, and that's combined with existing single flash facility that was discharging hot brine to the reinjection line. So we've been awarded for the let's say repowering with this bottoming unit that takes the brine before the reinjection and gives back to the reinjection line. So here the complexity is also dealing with high silica content. So we implemented also an AC dosing system to avoid the scaling of silicates. Going to the key part of the presentation about the innovation, I see two levels of innovation in geothermal industry. The first one is related to the drilling technique to extract the heat from the underground. And we talk about EGS, Enhanced Geothermal System, and AGS, Advanced Geothermal Systems. There is also another work stream that is related to the mineral extraction. In fact, getting lithium out of direct extraction from the brine can be very sustainable, but also very beneficial for increasing the revenues of the operation because of selling the lithium. And the first level of innovation is the one that definitely is putting geothermal in a very good spot for going big. So this is a first of the kind worldwide EGS project, commercial scale, the Fervo Cape Station phase 1. It's now under advanced phase of construction by Fervo and Turboden and its partner. It's based phase 1 on 3 ORC units. Each one is a 62.5 megavolt ampere generator. So the total ORC net capacity will be 108 megawatt. With 6 turbines, 2-level pressure, isopentane with working fluid, and the design temperature that was already also checked by Fervo in circulation test will be 200 degrees C. In terms of timeline, this project was awarded in May 2024, and the COD is expected very soon. So the commissioning will start by end of this year, and the first unit of the 3 will be put online by March next year. So stay tuned on this great milestone in geothermal environment. So I have a 30-second clip of how the site is now in the last picture of few days ago. So you see there are 3 units, and there is an advanced phase of construction for the air-cooled condenser, which is the long lead item, and the item that also takes longer time for the erection. The heat exchangers, you see, the turbines are on the way. So all the equipment has been procured now, has been shipped and or arrived at site, and is waiting to be erected before commissioning phase. The other technology I mentioned is advanced geothermal systems, so closed loop. You are definitely familiar with the Evor loop technology, and Evor is also a pioneer in this type of drilling solution. And I will show a picture of our Garrett Street 8 megawatt project that will be the first commercial scale project in Germany. So this is the power plant. 1 unit, 8 megawatt, with 1 turbine, based on 2-level pressure on a single turbine, isobutane, the working fluid, and the design temperature of 120 C. The first startup with the first loop is expected by October this year. So also here we are very close to turn on the light with first of the kind geothermal project. So going to the end of my presentation and taking courtesy of Fervo of this slide, what is driving this scale up and boom of geothermal projects? Definitely there is a big demand of power, of electricity, mainly driven by data centers, but also other type of industries that require base load and clean energy. And geothermal is placing himself in the top rank with in terms of capacity factors and low emissions. So it's basically even better than nuclear energy. And everyone knows that the potential is terawatts of power, and basically Western US has at the same time the best resources and best industry and know-how worldwide. So that's why everything is happening now in this side of the world. A quick off topic about data centers. In fact, ORC can work with a number of energy sources. This example show how ORC combined with, for example, a 100 megawatt baseload power rack of gas turbines, recovering the heat can increase the baseload of 30%. So adding to the 100 megawatt, it is always online to feed the data centers. 30 megawatt on top of this 100 is the heat that can be simply recovered by the waste heat after the turbine exhaust stack. So keyword scalability. Which are the advantages? And by scalability, I mean go big, go to 30, 50, 100 plus megawatt project, and let's say not focus on a 5 megawatt project as it was the trend probably before, 5, 10, 20 megawatts. So now geothermal is going big because it has a lot of advantages: the economy of scale and higher return of the investment. The efficiency increases. The larger the turbines, the higher the efficiency. Also, it is possible to, in a let's say phased project, you can start procuring ahead if you have a standardization, so you can shorten the delivery time. You can optimize the constructability because you have larger components, but fewer of them. So you have less installation activities. Levelized cost of electricity and operation cost reduces, and having a larger portfolio for sure reduces the risk because you can share and have lessons learned on repeating activities. And of course, you can attract bigger investors. That's what, for example, Fervo is doing. Of course, you have challenges because there is a higher risk capital initially required. There are some supply chain bottlenecks on some specific items, long lead items or generators that have reached for the 4 poles probably the largest frames available. Then you have to go to the 2 poles, but you need a faster turbine. So there is a sweet spot for let's say the 100 megawatt capacity for a single 4-pole generators. Transportability can become a limit, going bigger with the components, and also the supply chain for drilling. Of course, you need 20, 30 wells for such a large sites, so you need to plan ahead. So, conclusion: what can make really the geothermal industry scalable and more competitive? My answer is that what we are seeing is the best way to get there. So innovate on drilling techniques, EGS, AGS, but also combine them with a large scale ORC technology that is available in the market. And that's it from my side. Thank you.
Fantastic. Thank you, Joseph. So at this point, we will switch to Burns and McDonnell, and it is my pleasure to introduce Justin as an emerging technology manager. At Burns & McDonnell, Justin focuses on market and opportunity development for generation and decarbonization technologies. Throughout his nearly 20-year career, Justin has been focused on the development of generation projects. Prior to his current role, Justin managed Burns & McDonnell's development group, supporting power generators across all aspects and throughout the full project development lifecycle, from initial concept through implementation and operation. And I'd also like to introduce Derek Lester. As an engineer at Burns & McDonnell, Derek works within the decarbonization group, focusing on market and opportunity development for emerging generation and decarbonization technologies. Throughout his career, Derek has focused on the power generation space. Prior to his current role, Derek worked on the execution and development of conventional gas generation, including simple cycle and combined cycle power plants. Gentlemen, I'll turn it over to you.
All right, thank you, Carrie, and thanks, Joseph. It was good to see a lot of those updates on the Cape Station project and the exciting work that's happening there with Fervo and Turboden. I know a lot of eyes are on that project, and folks are looking forward to that continuing to progression. So appreciate that, and I think Joseph did a good job of kind of setting the stage from the surface facilities perspective and looking through what encompasses a project there. And we wanted to touch a little bit on some of the broader project development considerations, kind of certainly related to surface facilities, but kind of more of the tangential items that can really have some big impacts on the overall project development cycle and the project development timeline. So just to kind of start, to give a little background on who Burns McDonnell is, for those that maybe don't know, we're a global design and construction firm, about over 12,000 professionals and 75 offices worldwide, and very heavily rooted in the power generation and then the power sectors. Primarily a North American contractor, focus a lot in the US and Canada, but do have a presence kind of throughout the world, and in various different aspects there. And we're really focused in kind of all aspects of the infrastructure space. really mention, the power generation side, but touch on a lot of things from transportation, aviation, certainly power generation, power distribution and transmission, really kind of any infrastructure business, which kind of helps us to really get a good grasp and understand holistically when we're looking at project development on a lot of those factors that maybe are outside of the typical, fence line of a given project that can have some big impacts on the overall project progression. Within the power generation space, focused on decarbonization technologies in addition to conventional power generation, but really looking at certainly geothermal, but kind of all aspects holistically of moving towards a decarbonized generation industry, whether that's renewables, geothermal, carbon capture, nuclear, etc. So as I mentioned, kind of wanted to touch on some different aspects of the project development cycle and some of those factors that can have some big impacts to either the project progression, the project timeline, or sequencing. So touch a little bit on supply chain constraints, specifically some long lead equipment, and within the constraints of where the world is at today on how what maybe wasn't considerations years ago, or even more recently, now have big impacts on the project progression. Look a little bit at the electrical interconnection process and similar considerations on how that is driving a lot of projects, and why understanding that process is very important. And then touch a little bit on the permitting side, and specifically with NEPA, and how that can have some significant impacts on the project progression as well. So I'll turn it over to Derek now to go through the first couple items.
Yeah, thanks, Justin. So the first category we are going to look at is long lead equipment, and it does so happen that most of these items are electrical. These items are really where your engineering schedule is going to meet your construction schedule. The timeline you need to get to PO for these pieces of equipment are going to heavily impact your engineering manpower curves, and the arrival of these pieces of equipment to site are going to heavily impact your construction manpower curves and the degree of compression you're going to have in your startup schedule as you strive to meet your COD date. All of these markets really had a large whiplash effect that happened under COVID. But unlike other supply chains, these markets really haven't come fully back into alignment of where they were pre-COVID. And now that the AI boom is here, the dynamics that were already present in these markets, we're seeing further impacts from that additional demand. So the first category of equipment that we are going to talk about is high voltage breakers. This is on the transmission and distribution side of the fence of the project. These items are looking at about a 3 to 4 year lead time from issuing of PO. And the variance in that range really is correlated to the voltage of the breakers that you're looking at. If you're looking at 230 kV or on that slightly lower end, you're looking at about 3 years. And if you get up to about 500 kV on the high voltage breaker, you're going to be looking at about 4 years. Design considerations for these pieces of equipment. So the good news is there is less project definition required to reach PO with this equipment. You really just need to understand what type of generating capacity and voltage you're going to be transmitting at, and you should be able to issue a PO relatively quickly. That is provided you are working with an engineering and procurement partner who's used to buying these types of equipment. And then, like I kind of previously alluded to, if you have less project definition, maybe because you haven't done enough engineering to really define what level of generation you're going to have, you can buy with a little bit of margin and just kind of overbuy some capacity, but that is going to cost you additional dollars. The next kind of link in the chain that we have from an electrical perspective is the generator step-up units. These are large transformers that function with the purpose of basically taking the generator side voltage and stepping that up to the transmission and distribution voltage that's going to be required. You can have multiple arrangements. You can either have one per generator that you have on site, or you can tie multiple generators into one GSU to get all of that power up to grid level voltage. For these geothermal projects, you're going to be looking anywhere from 30 to 100 MVA, maybe even a little bit smaller. But for this range, you're looking at about 2 to 3 years for that lead time from PO to delivery to site. The things that are going to impact this lead time are threefold. So the MVA, the higher the MVA is, the longer the lead time is likely to be. That's because a lot of facilities may not have the capability to build these higher, larger sized transformers. So naturally, that market is thinner, which leads to a farther out delivery timeline. And then the other thing is voltage. So the higher voltage that you have on the high side of the transformer, there's just less facilities that have the capability to test those once they're manufactured. So there's a thinner market and longer lead times. And the third factor is the specificity you want out of the manufacturer that you're buying from. There are more established players that some clients prefer to only go with. And then there are kind of the second tier of players that have come into the market more recently and have less life cycle on their deployments. So depending on if you are open-minded or if you are more constrained on who you're comfortable with going with, that'll impact lead time as well. And then just to give some flavor to what the overall market looks like right now, on like large scale gas projects, the GSU is really becoming the thing that is setting project schedules. If you're looking at those blue chip suppliers, those tier one suppliers, and you're looking at over 150 MVA for like a big gas project, we're seeing lead times that'll go beyond 4 years in those cases. Similar to the HV breaker, the design considerations you have for buying a GSU, the good news is you're able to have less design definition in order to get to a PO. That's because you only need to understand the power throughput essentially, and then understand the MVA. And if you're working with an engineering and procurement partner that is used to buying this equipment, they should be able to get a spec out relatively quickly. And like with an HV breaker, you can also spend more money for a little bit more conservatism if you haven't fully defined your design at that point. The next piece of electrical equipment we have is the medium voltage switchgear. So this is kind of the key node that manages all the medium voltage circuits. They're going to be doing a lot of the heavy lifting on the project. Kind of the center of distribution, center of the heartbeats of the plant from an electrical perspective. The lead times for these, the good news for these is the lead times are only about 80 weeks at this point, but and then if you want to have a prefabricated PDC or power distribution center, you're going to be adding like 8 to 16 weeks on top of that. From a design perspective, there is more design required. You're going to need to have a pretty locked down PO or a locked down one line in order to issue that PO. You can play the game of trying to buy an MV switchgear without a really firmed up electrical design, but that can be a really dangerous game. You can try and leave yourself some outs with spare breakers and equip spaces, but again, you can get yourself introducing some difficulty down the road in your design process if you've boxed yourself in an inconvenient way. So really, it's good to define your electrical design before buying these pieces of equipment. Moving on, the next thing we're going to talk about is the interconnection queue and how that varies. So this is a map of various RTOs, ISOs, and electricity markets across the United States. The United States is really a diverse patchwork in terms of how we regulate electricity and how we structure markets and all those types of things. But specifically, interconnection varies from geography to geography. So we're going to talk about a couple of geographies that might be relevant to geothermal project development. So the first on one end of the spectrum is ERCOT. So ERCOT runs a first ready, first served serial interconnection study model, unlike cluster models, which we'll talk about later. So I like to think of the serial interconnection model as being kind of more simplistic, like the DMV. Once you come in with all your paperwork and you're ready, you're in line. And once the people ahead of you get done, you'll be up next, and then they'll study you. Right now, it's 18 to 30 months for interconnection or for the study to be complete, and about 4 to 4.5 years to reach COD after the request is in. These are some of the shortest timelines in the nation. Another benefit that some see in the Texas system is the connect and manage approach. So basically how this works is if you have an interconnection request, there are going to be network upgrades that are likely required in order to get your electrons that you're generating to market in all situations. So the connect and manage approach basically says you can connect to the grid as fast as you want to, but until we get the network connection done or the network upgrades done, if there is curtailment due to high demand or high production from renewables around you, you are going to be curtailed first. So it's a risk that you as the developer take on, but it also allows you to gain revenue faster and speeds up the process to interconnection. So in this market, you can plan for roughly a 2-year request or timeline from interconnection request to study completion. And at this point, you should have some assurance on how much capital you're going to have to deploy on the interconnection side, and you should be able to move forward to your final investment decision. Now, on the other end of the spectrum, we have CAISO, the California Independent System Operator. This is the ISO that covers most of California. So they run, up until 2008, CAISO ran a similar system to Texas, but in 2008, they had an increased volume of interconnections coming online after some deregulation, and they moved to a 2-phase cluster study model. So basically how that works is roughly annually, you will be put in with a cluster of other interconnection requests, and then you will be evaluated within 2 phases. So the first phase is really just looking at like high level, is there going to be a high level of congestion in this area for these projects? It basically offers a first off-ramp to developers that realize they aren't interested in that location because of the costs that are going to be associated. And then in phase 2, you get into the deeper modeling, the cost allocation, and what that's going to look like. And then after those 2 phases, you move into the general interconnection agreement. And this is a little unique to some other systems where the general interconnection agreement negotiation is actually a little bit more of a process in and of itself compared to other more standardized systems that are out there. So all of those phases that I just laid out contribute to the fact that expectations for current requests to COD and actual interconnection have gotten up to like maybe 8 years, and there isn't like a lot of clarity in those expectations. So cluster 16, which was supposed to be which is the 2024 cluster, has actually been postponed due to backlogs in the system. So basically, if you have missed the 2023 cluster, expectations are currently that if you submitted into that 2024 cluster, hopefully it'll be basically started in October 26 is what current expectations are. So if that goes optimistically, people are hoping that they can wrap up their studies optimistically by 2028. But if people drop out of your cluster, there are going to have to be restudies, and that is going to potentially delay the completion of the study even more. So basically the dynamic that's playing out in California to probably the worst extent in the country, but these dynamics are also seen across the country, is with the increase of lower capacity factor and lower scale renewables, basically you're having a problem of a lot of people putting in interconnection requests with a high quantity of them dropping out. And then when they drop out of your cluster has to get restudied to redistribute that cost allocation. And this dynamic kind of creates a cycle where it ends up feeding on itself, where because developers know that there's very long timelines for interconnection, they submit speculatively, and then more people submit speculatively and end up dropping out. So not a great situation in California with very long times and a lot of foresight and planning required in that market. So the next one I'm going to talk about is the Western energy imbalance market, specifically the portion of that market that is outside of CAISO. So CAISO participates in this market. They also participate in the running of this market. However, for the sake of this slide, I want to talk about the geographies that are not in an ISO that make up large portions of the attractive geothermal prospects in the Rocky Mountains. So the interconnection process for these geographies is very balkanized on a utility by utility basis. So each individual utility will actually run their own interconnection process, and most of them do an annual cluster study model. Due to this balkanization, historically, they've seen higher costs associated with actually doing the interconnection because they're not getting as much economies of scale, but they're also seeing more, they have historically seen more efficiency in getting to that study actually completed because they're more balkanized. However, timelines are starting to increase for interconnection in these geographies as well. You can expect around 2 years for a study in a good case, and maybe 4 to 6 years from request to actual COD. You're really just starting to see the same dynamics that you're seeing in California of because timelines are extending, there's an increase in requests that are speculative, and that leads to more dropouts, more restudies, more increasing of timelines. Justin, do you want to take it back?
Yep. All right. So just wanted to touch a little bit on the permitting process and the NEPA process. And for those that maybe aren't familiar with kind of what NEPA is basically it's the National Environmental Policy Act that was created in the late 60s by President Nixon. And really the intent of this was to establish a process for federal agencies that would require them to consider the environmental impacts associated with their works, with their projects. And so the reason why this is really important is that there are kind of 3 major triggers that would start the NEPA process, and one being if a project is occurring on federally owned land, public land, if a project has federal funding in some form or capacity, or if projects require some form of special federal level permitting. And so from a geothermal perspective, really it's the first 2 triggers that are primarily the drivers on this one, with the federal land considerations and then potentially federal funding considerations. And as you can kind of see from this map, the areas that are generally federal land correspond pretty closely with the areas that are, high likely and high probability for good geothermal resources, at least today, based off of, current commercially available subsurface and drilling technologies. But so the utilization of that federal land for geothermal projects then triggers the NEPA process, as well as, with here recently with the influx of federal funding, grant funding, things like that, has also required the NEPA process. Also looking at the fact that if the intent is for a project is to use, loan funding through DOE's LPO, that can also trigger the NEPA process. So a couple different considerations there that would require NEPA to be considered from a geothermal project. And so really what the NEPA process is, and I know this is a little bit of an eye chart, so don't necessarily need to pay attention to the details on here, but really what this is it's a process to work through to evaluate and understand the potential implications and impacts from an environmental perspective. And so really what happens when the NEPA process is triggered is there's kind of 3 different pathways that can go down, and variance being on the level of evaluation, study, investigation needs to be done to understand what the impacts are for a project. So on the low end of that would be what would be a categorical exclusion, which basically just requires documentation and moves through the process pretty quickly. And each federal agency has kind of pre-established categorical exclusions that if a project falls under the identified CEs, then you go through this kind of expedited process. The kind of second category would be an environmental assessment, or an EA, which involves doing some level of investigations to determine environmental impacts. And then on the other end of the spectrum is an environmental impact statement, which is a more comprehensive evaluation and investigation for the site-specific, project-specific considerations. So looking at this from an overall schedule perspective, and just kind of typical timelines ranging on the low end with a categorical exclusion, you're talking a few months, 3 to 6 month timeline typically. On the other end of that spectrum, if you have to go the EIS route, it's a multi-year process. And so understanding what the requirements are early on can have significant impacts on the amount of time that needs to be considered from a permitting perspective. And this doesn't consider additional permits that may be required from, local, state AHJs, things like that as well. From the geothermal specific timeline, this is looking at kind of overall project development timeline and based off of some DOE GeoVision analysis, that typically this could have been in the 7 to 10 year timeline when you would consider the fact that different phases of the projects would require to trigger the NEPA process. So initially starting with looking at the geothermal resource identification, and the NEPA investigations associated with that, then moving into progression to the production wells and the well field development, and then a separate requirement for the NEPA process associated with the power plant, as well as the lateral facility, the transmission line, switch yards, et cetera. Now, there have been some recent changes in the past several months with the new administration coming into office in January, where Bureau of Land Management in early this year finalized a categorical exclusion for geothermal resource confirmation. So the process to be able to identify geothermal resources and do those exploratory wells now has been streamlined. Does not negate the process the requirement to go through NEPA for other aspects of the project though. But kind of along those same lines, with the administration pushing the energy security and the energy emergency declarations from the president, the Department of Interior here just recently implemented some emergency permitting procedures specifically for some projects in Nevada to further expedite this permitting process. So trying to drive down the timeline to get through this investigation and permitting to be able to get projects implemented and operational.
Thanks, Justin. All right, so those are the three factors. Let's try and bring it all together. So this is a very generic surface generation only theoretical schedule for a geothermal project. This is a very aggressive schedule. Basically, I've taken the factors that we've previously talked about and I have used the averages for the durations, but then I have tied them in very aggressively to the activity that's occurring next. So if we kind of walk through this, we'll see that we have the long lead equipment coming in relatively late in the project lifecycle. Like on this theoretical project, you would definitely have some compression occurring in the commissioning and startup schedule in order to hold that COD date. And then an unrealistic assumption I've made here that's relatively aggressive is right the day you get done with NEPA and get your clearance, you're also breaking ground the next day. That's not a very realistic assumption. And then also once you reach the study completion for your interconnection process, you're also going to get full notice to proceed the very next day. Also a very aggressive assumption to reach final investment decision. So with that in mind, I think this schedule is still pretty useful. It really shows that you're on in an aggressive case. If you have a 4.5-year timeline for an EIS a project with NEPA and an EIS, a 4-year timeline if you're able to achieve an EA, and it really shows how you are going to need to start planning early and deploying capital relatively early in order to move the project forward and hold the COD date that you're aspiring to. So you're going to be doing engineering to do the definition that's required in order to cut POs for long lead equipment and write those specifications. You're going to have to do permitting activity. You're going to have to define the project through preliminary engineering in order to even initiate the NEPA and various other permitting processes. And you're also going to have to get involved and spend some time to navigate whatever interconnection queue you are dealing with. So what's going to be required for this type of project is a stage gate approach that is looking holistically at all these factors that can impact your ultimate COD date. So what are the solutions you're going to need? Well, to understand those solutions, first we have to understand what these three factors have in common. The first thing, they're all pretty complicated in their own way. They're all tough games to play. Navigating long lead equipment, navigating the interconnection queue, and permitting, they're all difficult things to do. But they are all required for all power project types, whether it's solar, gas, or geothermal. You're going to have long lead electrical equipment, you're going to have interconnection that you have to deal with, and you're going to have some level of permitting on those projects. Now, how are these factors different from each other? Well, the type of expertise that each of these factors require are all relatively different from each other. Navigating long lead electrical equipment and how that impacts a project, you really have to understand both the technicalities of what's required and what level of definition you need to buy this equipment. And then you also need to understand how that's going to tie into a very complex and overlaid construction and commissioning schedule, and how that's going to impact cost in the field and how that's going to trade off with your COD date. For interconnection, this is more of a pure consulting type service related to the power industry. That's kind of its own expertise in itself. And then permitting is a whole different ballgame that requires you to understand the federal regulations, the locality regulations that you're dealing with, and really understand what technical implications of a project impact the likelihood and ease of getting permitted. So naturally, with how different all these different factors are, there are firms that specialize in each of these individually. There are also firms that have all of these capabilities in-house. So as a project developer, you really have options of what path you want to take. You can take a multi-party approach where you as the developer are basically managing 3+ entities that are dealing with all these factors in the front end of a project. What this is going to take from you as the developer is a lot of expertise in surface power generation projects. This is going to take experience in understanding how to make all 3 of these factors dance together in a way that efficiently lets you meet the COD date you're aspiring to. And it also is going to require a significant amount of overhead in order to manage all 3 of these factors. When you're dealing with long lead equipment, when you're dealing with interconnection, or when you're dealing with permitting, there are times when there's going to be a lot going on in the early stages of a project, and there are going to be times when you are just waiting on the interconnection queue. So there's really a lot of up and down, and you're going to have to staff that through the life cycle if you're going to take the multi-party approach to make sure all these things are coordinated. The other alternative is you can take the one-party approach and go with a firm that has all these capabilities in-house. This is going to take significantly less experience in the power industry from your part as a developer. You're not going to need nearly as much understanding and in-depth experience of understanding how these 3 different factors need to play together in order to make your project schedule work. This party should be able to take that management significantly off your plate, and that's going to lead to significantly less overhead that you're going to have to staff on your part, which is going to be very beneficial to you. But regardless of what choice you make on that decision, it is imperative that you get started early, you identify the long poles in the tent, and you don't let them sneak up on you. Be prepared. Thank you.
Fantastic. Thank you, gentlemen. I am going to open it up to questions. We have a few minutes. I'm going to extend the seminar for a few more minutes just to make sure we get some of those questions in. I think we've had some amazing conversations today, and really want to thank our panelists for all of the fantastic information they shared with us. We do have one question for Joseph that has come in. Can you provide some details around the turbine in Germany?
Yeah, so that's a single turbine that is running on 2 different pressures. So there are 2 inlet lines going in the same turbine that was also employed in another project we have in operation in Germany. So it's a common practice and very efficient way to increase the efficiency of a single turbine when the capacity of the overall generated capacity is not that big. So that's a single 8 megawatt turbine running on 2 different temperatures and pressures, but with the same working fluid.
Okay, fantastic. Thank you. So I have another question. We both spoke to delivery delays on some of your equipment and some significant lead times. Is there something you can identify that would help with this process? Are there quantities or a change in raw material supply? It seems like there's an opportunity for efficiencies there. Do you have any perspective on that?
Yeah, I mean, I had a couple things on that. I mean, one, I think kind of Joseph touched on a little bit, but the ability to kind of standardize and to where you can order, multiples can help. One, you can kind of do some of that pre-purchasing if you know you're going to use them subsequently. The ability to leverage different suppliers. There's, as Derek kind of mentioned, you've got your typical kind of tier 1 suppliers. If you have ability or willingness to kind of look at alternative suppliers from that equipment or alternative sources of manufacturing, origins of supply, things like that. But really, I think a lot of it kind of comes down to, risk tolerance and planning. There's things you can do to progress when you place orders. but that requires concessions from a project definition perspective, potentially, and risk tolerance for spending money earlier on and cash flowing earlier on.
Got it. Thank you. All right, fantastic. So what do you see, and you both kind of mentioned those operation costs. Do you see what's your greatest opportunity to reduce your LCOE or those operational costs that you referred to? Any thoughts around that? How that could be more, that process could be more efficient?
Well, that's a question more for a developer rather than for a technology company or construction company, I believe. No, to me, the next generation developers are doing, that is to overlap the drilling phase with the power plant construction phase, is the best way to optimize the overall schedule. At the end of the day, that would result in earlier revenues. So also LCOE will benefit from that. That's my point. I don't know, BMAC, if Besmac have it.
Yeah, no, I mean, I would agree with that. I think, again, it kind of comes back to that overall planning. It's, identifying when you can do things, how you can do things in parallel versus sequentially. It's doing what you can early so that you can avoid surprises once you're in the heat of doing projects, so you don't have those unexpected delays. But anywhere you can identify opportunities to kind of progress and squeeze that schedule down is going to be big on the surface facility side. Doing things from a constructability and modularization. With working with folks like Turboden to be able to identify how you can do some of that, modularity and prefabrication and things, so you can reduce field schedules. I think there's opportunities. I don't think there's a silver bullet, but there's different opportunities to kind of pick away at things here and there.
Okay, fantastic. Thank you. So we have another question. How had the new Fed administration policies shortened the 7 to 10 I'm assuming year NEPA project timeline shown by Burns & McDonnell?
Yeah, so I'll say that, I mean, that timeline is very heavily dependent upon the project specifics. And so that 7 to 10 years, you could be outside that time frame just previously without any of the changes. But in general, if you look on kind of the front end is really where with the categorical exclusions for the resource identification and kind of resource development piece on the subsurface side. If you pull out and say you would have had to go the EA route before you could start doing your test wells and your exploration wells, if that's called a 12-month process, and now you can go the categorical exclusion route and do a 3-month process. I mean, there you've taken 9 months, give or take, out of that overall cycle. And so I think that's the front end of that is really where the focus has been. And then with some of those emergency procedures to kind of accelerate that overall process, I'd say you could probably be talking potentially a couple years or more out of that overall timeline. But again, it's very dependent. One project in a given site could trigger an EIS, which is a multi-year deal. That exact same project in another location could only trigger an EA, which would cut that timeline itself in half. So it's very dependent upon the project and site-specific considerations.
All right, fantastic. And I think that's the questions that we had. So thank you all for joining us today. And thank you again to our panelists for a fantastic webcast. And we look forward to seeing you at the next one in a few weeks. Thank you so much. Have a great day.
Thank you.
Thank you.